It's sort of a new system. The green light that is shining over there on the side of the room, if there were to be a shooter on campus or a dangerous situation such as that, that will go red and our doors will lock automatically and we're to stay put. If the shooter's in the room, it's a different story, but yeah, then we have to deal with it a little differently. But if that does happen, just stay calm, stay in the room. Again, these doors will lock automatically and we're pretty safe in here. But that would be the situation that that light is to warn us of. Okay. So anyway, I thought should mention that to you. Sadly, on college campuses, we do have to be prepared for things like that. So, again, I've been here for 12 years, and we had one bomb threat, turned out to be nothing, and that was really early on. That was over 10 years ago. So thankful. I mean, again, we're in an urban situation. We're right on the edge of a major urban area, so you always have to be careful. But we're trying to be prepared. All right. Well, let's talk about the rock cycle. Those of you who went on the rock walk on Tuesday, we sort of got started. Those of you who are coming today, we'll follow this up. We'll sort of supplement all of this. We will be able to make. They did shut down the tunnels, so we're not going to be able to go underground. But we can see all but one of the rocks that I'd like to show you above ground. So we'll still do the walk. And if you're coming on Monday, the same thing. You'll do the rock walk on Monday. So it used to be, and I probably, again, I could choose to teach geology and all of the topics of geology through the rock cycle. Right? Because every rock tells a story. And those stories are what happens in the earth, what happens throughout Earth's history, what's happening right now. Those stories can all be told from the rocks. Matter of fact, that's how we know all that we know about geology, is by studying the rocks and the layers of rocks in the Earth's crust. Now, typically, now that we have the unifying theory of plate tectonics to tie everything together through an explanatory framework, we start with plate tectonics. And that is still where we need to sort of start with the rock cycle. Even though, as I'll emphasize later on, it is a cycle. There isn't a start and a stop. It's constantly going, and has always constantly been going since the Earth formed. We usually start with igneous rocks because they form from magmas and are situated in the Earth's crust then by tectonic forces. So we have intrusions of magma, such as the batholith that we'll see on the rock walk. And if you remember us talking about intrusions, the various types of intrusions of magma that can push their way into the crust and then crystallize into solid rock. Some of this magma can reach the surface, however, and become lava. And on the surface, it cools much more quickly. We tend to then have a different texture between extrusive igneous rocks and intrusive igneous rocks. And so I'm going to use a lot of terms like that, and I'm going to use terms to describe texture, like coarse-grained or fine-grained, small crystals, large crystals. I'll use the word clastic quite a bit, which means pieces that are cemented together in some way. But we'll also talk a lot about the mineralogy. Depending on the heat of the magma, the temperature of the magma, it can have more or less minerals that are in the rock, because the hotter it is, the more minerals there are. If it cools under pressure, you can have more minerals. If it reaches the surface and cools, a lot of times those minerals will separate out into separate things. So we'll talk a lot about that as we go through each of these stages. But from igneous rocks, anything exposed on the surface of the planet is going to be eroded, weathered by water and wind and ice, gravity. All of these forces are going to cause the rocks to break apart into pieces, and the water can dissolve rocks into solution, and those pieces can then be carried away. That's erosion. Weathering is the actual breakdown of the rock into either pieces or into a solute in solution. Erosion is the movement of that material away from where the rock originated to someplace else. And then the deposition of that material leads to those laws of stratigraphy, those relative time that we saw in last week's lab. Those broad beds of sediment laid down in the oceans that are originally horizontal and continuous and in superposition. subsequently perhaps disturbed by other tectonic processes like intrusions and faults and things like that. So if you recall, we're tying everything together, in a sense, through the rock cycle. Sedimentary rocks are those rocks that form from those pieces of weathered material, whether they're cemented together in those big beds or whether they precipitate out of solution. We'll look at various processes there. Any rock, including igneous and sedimentary rocks, can also be recrystallized, not melted completely, but recrystallized under pressure or near heat and become a metamorphic rock. Metamorph meaning, changing shape. So, metamorphosis is not just something that you hear in geology, but the term should be familiar because it's a common term. So metamorphic rocks have changed their texture. They haven't changed their composition, though they may have changed their minerals. And we'll see a dramatic situation of that on the rock walk, where we see clay minerals become garnets. So metamorphic rocks are the third group. Now, also any type of rock, metamorphic rocks, sedimentary rocks, even previously existing igneous rocks, can be buried or subducted and remelted. Igneous and metamorphic rocks and sedimentary rocks can all be lifted up into mountains and then weathered again. Metamorphic rocks can undergo a series of metamorphoses where they change more than once. All of this is a cycle and is constantly going. And that's why the arrows don't just go in a circle, but you can go from igneous to metamorphic, and so the purple arrows go over here. And you can go from igneous to sedimentary, that go up there. You can go from sedimentary to igneous if they're subducted, and so we've got arrows that come down that way, and on and on. And all the terms that are along these arrows are things that we're going to want to look at. Crystallization of minerals into igneous rocks, the consolidation of this buried material being compacted and then cemented together, the exposure of material to weathering, either through uplift or other exposure. Erosion can also expose things. The transport or erosion of material from where it's weathered to somewhere else, and then the deposition into a layer. Lithification is a term that means turn into rock, become solid rock. You go from being sand to sandstone, from clay to claystone or shale, and that's lithification. And then metamorphism, which includes a recrystallization, and eventually rocks can be remelted. So all of these processes, all of these stages tell us, we can see the evidence of this when we look at the rock. One of the first things we want to look at when we look at a rock is what minerals does it contain, because this tells us a lot about how the rock formed. There is a distribution of elements in the solar system. Again, when we talked about the formation of the Earth, I alluded to this a little bit. That's how we've got the composition of the Earth's crust that we have. As the Earth accreted into a planet, it collected a proportion of that material that was in the original nebula, and the lighter materials rose to the crust. And we can see the percentage of things that are in the Earth's crust, and I'll show you this in a second. And it makes sense. It fits with that model. It's a big piece of where that model comes from, actually. And then we can start classifying these minerals. We can start saying, okay, we can recognize that there are some patterns here. Some of these minerals are made from silica and oxygen. These are the silicate minerals. Some are made from ions that precipitate out of solution, like the carbonate minerals. And we'll look at a few of those groups in a minute too. I also like to always point out that these minerals tend to exist on the surface in solution. Again, water is a constant. These minerals, these rocks are constantly exposed to water, and so a lot of times they're in solution as ions. We'll come back to talk more about ions and what I mean by that later in the course, but I'll show you the Earth Scientist periodic table here in a second, just to emphasize that the real world isn't quite as simple as we always portray it in a class like this, because I'm having to simplify pretty much everything that I describe so we can discuss it. And anyway, so there's that. This is how we know when you look at a star or you look at really anything that's burning, you know what it's made of by looking at the spectra that are coming from that flame or that star through a diffraction gradient. and it diffracts the light into various wavelengths that are representative of the different elements. So when we look at a distant star, we can do this. We can tell what the star is producing in its core, the fusion. The results of that we can look at. Now we're getting to the point where we can even do this to other planets and start to look at where there's water perhaps on other planets, where there may be other... now this has to be emitted light, not reflected light. So that's a challenge with a planet somewhere else. But this is how we know those kinds of things. And it's very reproducible in the lab setting. And that's how we start with what's the Earth made of and what would we expect the Earth to be made of. Again, using that nebular hypothesis, looking at what stars are made of and what they would produce during a massive explosion, what materials would then be in that original nebula that would condense into the terrestrial planets. And when we match that up, it matches really closely. This is what our crust is made of. And you'll notice two primary elements here, silica and oxygen. And they combine into minerals like feldspar and quartz. These are called the silicate minerals because they're made of silica and oxygen. There's actually quite a few of them, but these are rock or minerals that don't tend to dissolve in water. They're covalently bonded, they're bonded really tightly together, they make crystals that don't dissolve in water. But there's a lot of other things like calcium and potassium and magnesium and even aluminum and iron that can form ions in solution and then make other types of minerals from there that can be precipitated out. This isn't a list of everything, but these are the big things. There's a lot of other stuff that's just too small of a percentage to see here. But even though something may be a very small percentage, the mass of the crust, how big the crust is, there may still be tons and tons of those materials, like gold and silver and uranium and on, right? The entire periodic table. The rare earth elements, iridium, rubidium, things like that we can find and mine. It's just a very small percentage. But these are the major constituents. And so when we look at them as a group, and again, I'm not going to list every mineral group. I've mentioned two sort of primary ones, the silicates and the carbonates, because we're going to see over and over again silicate minerals in the rocks that we see on the rock walk, and we see limestone a lot on the rock walk, and the marble that is the metamorphic form of that. Those are carbonate minerals, calcium and carbonate, that are in ocean water and combine into a mineral when it precipitates out, when the oceans evaporate, that kind of thing. But there are a lot of others too. There are oxides, for instance. Oxygen can react with iron, form oxide minerals, can react with other things to make a number of oxide minerals. There are other minerals that come out of solution, not just carbonates, but sulfates and phosphates and a lot of different things. So the point is there's sort of two ways that molecules form. One is to be tightly bound together by sharing electrons, and one is to be loosely bonded together by different charges. Those ionic bonds form one kind of mineral. Those can dissolve in water. The tightly bound minerals don't dissolve in water. Water is not strong enough to pull them apart. So we see in any body of water both physical pieces and solution of solute. So we've got all that material in any water that's flowing off of any stream or bayou. You look at it, how muddy it is. That's what the mud is. It's minerals. It's mostly clay in this case. Those are silicate minerals that have eroded from igneous rocks somewhere else. Now, if you had to identify a mineral, and this isn't a geology class, but I know I've been told often that people who take this class have taken a geology class. And so you're familiar with this process of trying to identify minerals. How can you tell one mineral from another? Because I could show you some minerals that would be very hard to tell the difference just by looking at them. Quartz and calcite can look very similar, but they can also look quite different. You might even not be able to identify all the types of quartz because they can range in color from red to blue to yellow and orange and so on. Same with calcite. So how do you actually identify one from another? And I'm not going to require you to do this, but I just wanted to at least run through the ways that we can identify minerals. And there are a lot of visual things that you can do, that you can apply. But there are also some things that you would have to look at either with a microscope or an electron crystallography, basically looking at the crystal structure, X-ray crystallography, or some other test. Chemical composition, for instance. Now, a mineral is a naturally occurring compound or element. There are minerals that are one element, like gold. Gold is a mineral, and it doesn't form compounds. It's just gold. And there's a reason for that. And we can come back to that when we talk about chemistry. There are a number of other elemental minerals, but most of the time these elements are bound in compounds, and those compounds occur frequently, and we call those minerals. But we can look at the chemical composition, but it's not even that. It's not quite that simple. You can have different minerals with the same chemical composition, but different crystal shapes. And the best example of that is graphite and diamond. Graphite is a very soft form of carbon. It's just carbon, but the crystal shape breaks apart very easily. You can use it as a pencil lead. It's because it's soft enough that when you rub it on something, it actually breaks that part into a powder that's left behind as a mark. Diamond, on the other hand, is the hardest mineral that we know of. It's just carbon, same as graphite, but the crystals are bound together much more tightly and are hard to break apart. You can break them along certain faces, which is similar to, not exactly cleavage, but that's something that is also part of a mineral. If you can break it in a smooth plane, that's called cleavage. You've cleaved the crystals apart. If you try to do that and it breaks or shatters into a rough surface, that's fracture. And some minerals will cleave in some directions and fracture in others. Mica is a good example. If you've ever seen those really thin sheets of mineral that will peel off one sheet at a time, but if you try to break it the other way, it breaks. So it's got cleavage in one direction but not the other. Some minerals have multiple axes of cleavage and some have none. So these kinds of things can be used to compare, and so you can delineate graphite from diamond, for instance, that kind of thing. But all of these require generally something more than what we could just do in a lab by looking at just by looking at it in your hand. The things that you can look at are luster, for instance. Is it metallic? Is it dull? Is it shiny or dull? Does it look sort of opalescent? These are not real scientific terms, but they're descriptive enough that we can get a sense of the luster of a mineral. Its color is really not a very good indication of anything, because color can change. There's a mineral called hematite, for instance, that is bright silver, shiny mineral until you streak it on a plate and you rub it against a streak plate, and it leaves behind a reddish brown streak or mark. And that's because the real color of the mineral is reddish brown. But when it's exposed to oxygen, it oxidizes into this silvery color. So you can find it in both states. You can find it in its natural color, or you can find it as a shiny silver metal, silvery looking thing. It isn't iron ore, so it is metallic. But that, again, it gives you an indication. There are also some special properties, like magnetic rocks. There's magnetite, a mineral that is magnetic. So if you pick up a rock and a magnet sticks to it, you've got magnetite. Some fairly simple tests, but anyway. Oh, one thing that I thought it was going to pop up was Mohs scale of hardness. I'm not sure why it didn't pop up. Most of you are somewhat familiar with this. We can rank minerals by how hard they are. I mentioned graphite, very soft. Matter of fact, it'll leave a streak on paper. Gypsum and talc, other minerals that are very soft, and so they have a number on Mohs scale of hardness around 1. Talc is the mineral usually used to indicate that. You can scratch these minerals with your fingernail. Gypsum, you can scratch gypsum with your fingernails. It's softer than your fingernail. But when you get up to about 3, then your fingernail is softer. Calcite will scratch your fingernail. You can't scratch off calcite. That's a 3. So there's a simple test. Use your fingernail. You can also use a penny, copper, or a nail, or a piece of glass. These various familiar things have hardnesses that can be used to relate to a mineral. And you've often heard, a diamond can scratch glass. So one way to if you've got a fake diamond that's made out of paste, this would be more of a problem than it is now, because now we make fake diamonds all the time, or very similar crystals that appear to be very similar, that are very similar to diamond. But you would take the fake diamond and try to scratch glass, and if it wouldn't scratch glass, it was a fake. If it would, it's diamond, right? Because diamond is harder than that. So again, it's just a way of looking at, using some familiar things to look at all this. Again, I wish I had a periodic table in the room. I usually do. But you've seen a periodic table, and this doesn't look much like it, does it? We've taken all the elements, and we've mixed them up in different ways, because what we've done here is said these elements form compounds, these elements form ions, we've got inert elements that don't react with anything, and the common ions in the Earth's surface, in the Earth's crust, are not necessarily elements. They're compound sometimes, like carbonate, which is carbon and oxygen in a specific combination. So I don't expect you to see much in this other than I just want to make the point that the Earth doesn't exist in such simple state as what we try to present. So if I were to give you a box of minerals, for instance, and say, okay, identify these minerals, I would pick the easiest ones to give you, the best examples to give you. If I were to send you out into the environment and say, go find these minerals, that would be a much bigger challenge, because it would be very difficult to find them very simply like that, separate and in such clear crystalline shapes. They're embedded in other rocks. They have to be broken out or dissolved out or mined out. Most of the metals that we get come in ores where they're combined with other things, and you have to melt it down and then one at a time cool it down slowly enough for the metals to crystallize back out separately from each other. I've got some ores in the lab that have zinc and iron and lead and copper all in the same rock. You melt it down, cool it down slowly. They each have a specific point at which they crystallize, and so you can separate the metals out. So it's really quite an amazing thing that our ancestors developed from the Stone Age to the Bronze Age, by being able to smelt out these specific metals, to separate the copper and the tin from the rocks, from the ore, and then combine them into an alloy to make bronze. And then iron, to be able to smelt that out of rocks, and then use it to make, plows and other stuff. Okay, I guess I do have these coming up. There are 6 basic crystal shapes. Again, I won't go through them very easily. Sometimes, though, you'll see something that looks like one crystal shape, but it's a trick. If you look at it with X-ray crystallography, you realize it's a combination of crystals into that familiar shape. Anyway, I don't go into too much detail. But even crystal shape, when you're just looking at it in your hand, can be tricky. Again, there's types of cleavage, and here's most scale of hardness. And you'll notice, again, I mentioned talc, gypsum. You can scratch with a fingernail. Calcite, you cannot. Calcite will scratch your fingernail, but it will. A copper coin will scratch calcite, but not fluorite. Apatite will not scratch glass, but microcline will. Same thing with a nail, usually. A nail will scratch microcline, but not quartz, and so on. So these are the harder ones: diamond, corundum, topaz, those kinds of things. And so you've heard of many of these. If you go to the Museum of Natural History, for instance, there's some really nice fluorite crystals that show up in geodes, the purple fluorite. Anyway. It's interesting. And they're collectible, right? Some of these are considered gemstones. Some of them are very valuable. Some of these are the same mineral, but we call them different gemstones depending on what color they are. Now, there's a whole group of emeralds that include sapphire and rubies. They're all the same mineral. Depending on what color they are, we call them a different gemstone. All right, let's talk about igneous rocks. These are the rocks that cool directly from magma. But this can happen in a number of ways. And in fact, not all igneous rocks cool from magma. Some are just blown out of volcanoes as ash and cinder. But they're still volcanic, therefore igneous rocks. Let's talk about intrusive igneous rocks first, and then we'll get to the extrusive igneous rocks. Intrusive igneous rocks cool within the Earth's crust. They don't reach the surface. Now, because they're still underground, they tend to take longer to cool down. On the rock walk, I'll talk about these rocks cooling at higher temperatures, which doesn't seem to make sense. But when you add pressure, okay, that changes the temperature at which something will crystallize. And so they'll crystallize at higher temperatures. This will allow for different mineral combinations. If it cools on the outside, it takes longer. It cools at a lower temperature, you get bigger minerals, but you get fewer minerals in the rock. If it cools on the inside, it cools at a higher temperature, but also much faster. You get much smaller crystals, but you get a much denser, mineral-rich rock. Extrusive igneous rocks are those that actually reach the surface and cool on the surface, either in air or in water. So they cool very quickly and tend to have either very fine-grained small crystals, or they become glass. They cool too quickly to form crystals at all. And that's what a glass is. A glass is a rock that cooled so quickly that it didn't have time to form crystals, and there are various volcanic glasses. Ash and cinder form what are called pyroclastic igneous rocks. Sometimes the ash and cinder is mixed with some lava, and we get rhyolite. Sometimes it's entirely ash and cinder, and we get tuff. So let's take a little bit closer look at these series. I always like to show this, and again, this isn't something for you to memorize, but just to use as an illustration, that the mineralogy of a rock depends upon two things: where the magma came from and how quickly it cooled. The right side of this shows different types of rocks that can form by what's called a continuous series. In other words, it just cools continuously. It doesn't cool and then starts and stops. That's what happens on the other side. We get a discontinuous series. And you get a particular type of rock that forms over here. So high temperatures, if the rock is under a lot of pressure and cools at a high temperature, or crystallizes, I should say, at a high temperature, you can get these minerals in it, like olivine. You don't see olivine in granite because it cools or crystallizes at a lower temperature. Okay? You can see it sometimes in gabbros, and we'll see one of those. Well, we won't see it on the wall because it's underground. But anyway, so the various types of rocks that we can see, from granites to basalt, and I'll talk more specifically about those as we go, can be related to how they formed and what temperature they crystallized, at what temperature they crystallized. You will notice here's quartz and mica and feldspar. These are the common silicate minerals that we find in granites, and we'll see quite a bit of them on the walk. All right, let me go back though just for a second. I want to mention what these rocks are. This is granite. Again, we'll see it on the walk. That's Texas rose, the pink granite from Central Texas. This is a diorite, a little bit smaller crystals, but also part of the batholith below where the granite forms. And then this is a gabbro. The innermost part of that can be black. It's not always that obviously crystalline, but it can vary. We've also got, these are volcanic glasses. This is obsidian, scoria, and that's basalt. Basalt is the most common rock in the Earth's crust because it forms the ocean floor. So extrusive igneous rock pillows out of mid-ocean ridges and sea mounts and then forms the ocean floor. Very dense, that's why the ocean sinks a little bit deeper in the mantle and makes ocean crust subduct under continental crust. So here's our plate tectonics again, a big part of that. This is a rhyolite, which is a mixture of ash and cinder and lava. And this is a tuff, made entirely out of ash and cinder. There's also pumice, which is a volcanic glass. You may notice that scoria and pumice have holes in them. They cool so quickly the air bubbles get trapped, and that leaves the holes behind. And again, we won't see that one on the walk, but you've seen it either in landscaping or in a fireplace or a gas grill or something like that, because they hold heat really well, so they work really good in the fireplace. They're volcanic rocks, right? All right. Let's move on to sedimentary rocks. Again, when I classify sedimentary rocks, and you may have noticed one thing I might do on a test is ask you to identify some things in rocks, not the rocks themselves, but show you an igneous rock, for instance, and say, was this extrusive or intrusive? You can tell that by its texture. If I show you a rock with holes in it, like that scoria, you know it's extrusive. It's a volcanic glass. It cooled very quickly. If I show you granite with lots of big crystals in it, you know it was intrusive. Had time for those crystals to get big enough to see them. With sedimentary rocks, there are two types, somewhat similarly. There are those that are made from pieces of other rocks, and those pieces are pretty obvious. You can see those pieces. These are called clastic sedimentary rocks. Sandstone, shale, But there are also unsorted sedimentary rocks called conglomerates and breccias. These sediments tend to get separated out as they are carried by water because the big ones are heavier than the little pieces. So as the water slows down, the big pieces fall out first, and then the smallest fall out last. So you get sandstone, various grain sizes, siltstone, and then claystone, and they're separate. They're sorted. During floods or ice flows in a glacier, you get deposits of unsorted material, and they can come together to form a conglomerate. Basically, concrete is a conglomerate. You have a question?
Can you explain what extrusive is?
Yeah, extrusive for the igneous rocks is formed on the surface of the earth. The lava shoots out of a volcano, or the ash and cinder out of a volcano of some sort, and then collects on the surface or in the ocean. It's on the earth's surface, so that's extrusive. It's extruded. Intrusive igneous rocks intrude into the Earth's crust but don't reach the very surface. They cool within the Earth's crust. They're intrusions, so they're intrusive igneous rocks. The other type of sedimentary rock, other than clastic, are chemical sedimentary rocks. And these are the ones that form from material that was dissolved in water. So those ions, all the ions in the Earth scientist periodic table can form these kinds of rocks. There are some of these rocks that are just one mineral, like limestone, which is just calcite. That's the only mineral in it. It's calcium carbonate. But because it's so abundant in the Earth's crust, it's both a mineral and a rock. It's a rock formed from one mineral. Most rocks have more than one mineral. But if we look at sandstone, for instance, you'll see quartz and feldspar, just like you do in granite. So we'll talk about that story. There's a story there. Granite forms, has these minerals in it. Weathers into pieces, those minerals collect into a bed of sand, and we get sandstone. Same minerals, different texture because of the different story that they tell. The chemical sedimentary rock can either precipitate out of water as the temperature changes or evaporate if the water evaporates completely. Think of salt. Salt is a rock, right? And when the water evaporates, the salt is left behind. Gypsum is a salt. There are a lot of other salts, essentially, that are made from two ions sticking together when the water evaporates. But also organisms can take these chemicals out of the water and make a shell. And then the shell can be deposited in the ocean floor and make limestone or chert, depending on what the shell material was made out of. Typically limestone, because calcium carbonate makes a good shell. So that same mineral again, calcite. Organisms that use calcite to make a shell and then die and collect on the bottom form a limestone called coquina. Yes?
You know how you said that some of them, they form underwater, under the ocean? Do people actually, go there and get them out, or is there other places where...
Well, for the most part, we wait. There's plenty of them lifted up into mountains, and we don't have to go in the oceans to get them, because this has been happening for a long time. And there's plenty of these rocks that have been lifted up into mountains, and we just go blow the side off the mountain and mine them out, right? There's various types of mining. You can dig a mine shaft and then keep working on the walls and dig the rocks out that way, or you can strip mine the surface of the ground off and then just keep digging the hole basically and get that material out that way.
The mountain fall one time, one day because you're digging so much under it?
It's always a danger, yeah. That used to be a bigger danger than it is, but even lately, we've had those kinds of situations where people have been trapped underground because of those types of collapses. It's a dangerous occupation. Coal mining as well. Coal is actually a bioclastic sedimentary rock, right? It was organic material deposited into these beds and then compressed into a rock. We dig that back up and burn it, because it's mostly organic material. So mining is another issue. How do we get these materials out of the earth? One thing that I didn't mention with the igneous rocks, when there's an intrusion, sometimes there's cracks and things in the rock around it, and so veins can stick out from the intrusion, and when that happens, they can oftentimes be just one mineral or just a few minerals, and so that's how you find gold and silver and things like that in veins. But most of the time, especially today, you don't find gold veins very often. You find rock that has maybe 0.01% gold in it, and you crush it and you process it and pull that 0.01% gold out. But there's enough rock that you can get a bar of gold out of a ton or two of rock. It may sound like it's not worth it, but it is, because that bar of gold is worth, a lot of money. So it actually is worth it. But yeah, I mean, that's a whole other issue. And again, I'd love to spend more time talking about ores and mining and things like that, because there are environmental issues to consider. Again, strip mining, I grew up in Kentucky where strip mining was a big issue for coal, because it just devastated the landscape, right? And you just literally go in and here's a pretty mountain. Oh, look how pretty it is. Whoop, take it away, because there's coal underneath. And all of a sudden now you have just this big hole in the ground. And when they're done, they're supposed to go back and fill it up and put the trees back and make it look nice again. So I make a little bit light of that, but again, it's something that all of us have to consider, what we're willing to tolerate for the sake of getting, the energy that we need. Again, these are fossil fuels. They're coal and oil that are bioclastic sedimentary rocks and remnants, either fluid, liquids, or gases from that process. All right, let me take a quick look at some of the examples of classic sedimentary rocks. As I mentioned, there's different sediment sizes, from boulders to cobble to pebble to various types of sand, coarse to fine-grained sand, and then there's silt and there's clay. So if you get a mixture of these things together, you get conglomerates and breccias. These are a mixture of pebbles and boulders and sand and silt, all mixed together. But as you start separating them out, you can get different types of sandstone. You can get siltstone, mudstones, clay stones, which we call shale. Again, I'm not going to be quite as specific as this is, but it is something worth, you'll hear me say shale or sandstone and things like breccia on the rock walk. And that's where these terms come from. As for the chemical and organic sedimentary rocks, again, it depends on where they've originated from and how they've formed, but you tend to get either evaporites, minerals that are left behind when water evaporates, like salt or gypsum, or you can get things that are pulled out of the water by an organism or precipitate out due to changes in the ocean temperature or changes in depth and things like that. And this is where we get various types of limestone, dolomite, and then the organic materials at the bottom. Now, chert is an interesting one. If you look at chert, it doesn't look like a sedimentary rock. It's made out of silicate minerals, but that's because there are some organisms that use silica to make shells, particularly in very cold waters. And if it's cold water, that silica can collect on the bottom, but the carbonate will not. It will be dissolved back into the water. So again, it can get fairly complicated, but I don't intend it to be too complicated. I just want you to recognize when I use the term limestone, for instance, that I'm talking about a chemically formed sedimentary rock. The third group, and again, I do these in this sequence for a reason, but it's not because they come in this sequence in the Earth's crust, because it's always continuous. But metamorphic rocks are the rocks that are formed by changing a pre-existing rock, changing its crystal shape, changing the texture from fine-grained to sometimes banded with different distinct colors, like in a gneiss. And you'll hear me use that term on the rock walk. Depending on what rock you start with, you can get a very different metamorphic rock. So it doesn't have the same classification system as the previous two groups. It's a little more complicated than that. But there are a few things that are pretty straightforward. Like if you start with calcium carbonate and you put it under heat and pressure, so you take limestone, put it under heat and pressure, the calcite recrystallizes into bigger crystals and you get marble. That's it. Limestone goes to marble. Sandstone, heat and pressure, recrystallize into quartzite. That's about it. But if you take shale, for instance, and you put it under heat and pressure, some heat and pressure makes the minerals start forming layers, and you get slate from shale. But if you keep putting that slate under more heat and pressure, eventually those minerals migrate into wavy layers, and it becomes a schist. And that's a term used to describe the texture, because that rock can also form from granite. If you take granite and put it under heat and pressure, the minerals migrate into wavy layers, and we call it a schist. If you continue to put either of those rocks under heat and pressure, even more heat and pressure, those wavy layers can separate from the light and dark minerals and form bands. And that's when it becomes a gneiss. So a gneiss can form from shale, or it can form from granite, or it can form from a few other things. But those are the two primary stories that I always like to tell. This can happen in a couple of ways. Again, either it's just being buried, right? And the deeper it's buried, the more pressure is on it because there's a lot of stuff on it, weighing it down, pushing down on it. That pressure can cause metamorphism. That's called regional metamorphism. Or you may also have a rock that's exposed to an intrusion or nearby an intrusion. If it's right adjacent to the intrusion, that's a lot of heat and pressure. And you're going to get what's called contact metamorphism. A little bit farther away, you can still get the effects of that heat as regional metamorphism as well. So these various ways of forming metamorphic rocks are in this diagram right here. So again, I don't know why I didn't make it bigger. And we'll talk a lot about this. We'll talk on the rock walk because we're going to look at intrusions. A couple of intrusions that push their way into existing rock. All right, so just as a way to sort of summarize this all up, as I mentioned, you can look at each of these rocks and look at texture and mineralogy and pretty much identify one rock from another. Right? Again, I'm not going to require you to do that, but I'm just telling you can do that. So as a geologist, if we were out and about and you say, oh, what rock is that? I would take a close look and I might say, well, based on its texture and mineralogy, I think this is probably a blah, blah, blah. There's no rock called blah, blah, blah. There is a couple of very interesting rocks on the rock walk that tell these really intricate stories that are really interesting. And I will tell you the story of the last one since we're not going to be able to see it. It's underground and I haven't been able to find it in another accessible place, and the tunnels are shut down. On the rock walk, before we get to that point usually, you've seen 2 or 3 other rocks that have very intricate and long stories. And this rock looks like some of them. It's a gray rock with pink and red and white pieces or chunks in it, and little black and white circular pieces in other places. And it's got green mineral called glauconite squeezing in between some of these pieces. And so you look at it and you think, oh, this is like that other rock we saw. When in fact it's not, because those pieces are algal reefs rather than calcite that formed by recrystallization. They were parts of a stromatolite. If you remember in our hopscotch through geologic time, we saw stromatolites appearing at about 2.5 billion years ago, which are algal reefs. And this rock, these were in a lagoon. Tidal energy came in, broke them apart into pieces, distributed them into the mud, along with the glauconite that forms in lagoons because organisms are defecating, and that mineral mixes with the sands and makes glauconite. And shell fragments, pieces, those little circular black and white pieces. They're all mixed together into this limestone, for black, really to be about the closest we can call it, because most of it is carbonate, but it's very muddy and a lot of clay, and so it's really hard to classify. But because they're shell material, I know it didn't undergo metamorphosis. So it's not a metamorphic rock. It looks like the metamorphic rocks that we see earlier. So those kinds of things, you have to really look for the evidence in the rocks to tell you the story. And there are some geologists that are very, very good at this, a lot better than I am. And it's fun. I have fun. If someone shows me a new rock, I've got a bunch of rocks in my office. There's one in particular I've got sitting there that is extremely hard to explain, even for very seasoned geologists. I think we have a good explanation for it, but I'm not positive. All right, so let's do the quiz. Everybody has the book now, right? I had one more email saying they had just gotten it, but hopefully everyone by now has able to do this. So you can catch up if you got it late, but we're getting ahead of our quite a few quizzes under our belt by now, so I don't want there to. It's going to be harder to catch up if we go much further. All right, rocks that form by recrystallization of existing rocks are sedimentary rocks. False. Those are metamorphic rocks. The recrystallization of existing rocks form metamorphic rocks, so this one's false. sedimentary rocks formed from pieces of rocks weathered physically are called clastic igneous rocks. It's almost, it's not meant to be a trick question, but it's almost all the way up to the end. Okay, I'm expecting this to be true, and then, oh, igneous, no. I just said sedimentary rocks formed from pieces, so if you just break sedimentary rocks or igneous rocks. No. Maybe a little bit of, this is like diagramming a sentence kind of thing, right? Pull this out, basically we're saying sedimentary rock, that's not true. Sedimentary rocks that are formed from rocks weathered physically are clastic sedimentary rocks. They're not clastic igneous rocks. All right, so a little bit of a tricky one there. If the metamorphism is extreme, the crystals in the metamorphic rocks will migrate and form layers or bands, and these are called foliated metamorphic rocks. I didn't use that term, but I did use the term bands, and that's true. That's what we call those, bands, foliation. So these are foliated metamorphic rocks. This one's true. Number 4, rocks that form from magma, lava, or pyroclastic material are metamorphic rocks. This one you know. That one's false. Those are igneous rocks. Magma, lava, pyroclastic material. These have cooled, anything that cools directly from a magma or lava or is ejected by a volcano is an igneous rock. So this is false. And again, most of these, you'll notice my pattern here. It's just, I'm just tricking you with the last term here. And number 5, minerals are naturally occurring elements and compounds in the earth. This is an interesting one, because by definition, yes, this is true. Now, if we make a diamond, it has the exact same chemical composition, the exact same crystal structure, all of its properties are exactly like a naturally occurring diamond, but is it a mineral? By definition, no. A man-made diamond is not a mineral by definition. So we're getting to a point where we're now able to make these minerals, but technically they're not minerals, which is some sort of interesting. When this definition was made, we had no capability whatsoever to actually make a mineral ourselves. I mean, it required the Earth's processes to do this. It was difficult. You had to have extreme temperatures to make these minerals. Now we can make them, but we still have this definition. Minerals are naturally occurring elements or compounds found in the Earth's crust. That is true.
So the man-made ones and the ones that are made by Earth are still identical, right?
What's that? The man-made ones may be just as pretty, just as durable. They typically don't cost as much unless someone's trying to, perpetrate a fraud, because they're not naturally occurring. Now, the flaws in some natural diamonds are what make them most valuable sometimes. Actually, some slight flaws can give them better color, better sparkle. But even so, you can, there are various companies that sell fake diamonds like that are actually diamonds but man-made instead of natural. Someone can, I can't, a true gemologist could. Again, because it's the lack of flaws. But you'd have to have a special equipment to see it.